Number 21. Once again, I'm not putting up a filling diagram because at this point I'm hoping you're gathering that we do need to be able to figure out the order of the orbitals without actually having a filling diagram, just simply using the periodic table and knowing that these are the period numbers and that this is the S region, the D region, the P region, and this one's an S. Okay, so let's see. They tell us that it's sodium, which is fantastic because now we know sodium's electron configuration would be 1s2, 2s2, let's see, 2s2 is there, then we come across to 2p6, and then we come down to 3s, and you notice there's only one electron in the 3s. So I think that this would have the highest binding energy because it's closest to the nucleus, and that would have the lowest. So if we come down here on the high binding energy end, then that tells us right away that this is the 1s, and there's 2 electrons in it. This is the 2s, right? And there's 2 electrons. This is the 2p, and there are 6 electrons. And this must be the 3s, and there's only 1 electron representing that tiny little peak. So identify the peak in the photoelectron spectrum that represents the binding energy of the 2s orbital. Well, I think based on what we labeled up above, that should be pretty obvious at this point. Identify the peak in the photoelectron spectrum that gives the binding energy of sodium's valence electrons. You remember sodium has 1 valence electron in the 3s orbital, so I think that's probably going to be D. Which peak in the spectrum of sodium shows electrons closest to the nucleus? That would definitely be A, right? Because we're saying that the 1s's are closest to the nucleus. Which peak in the spectrum of sodium represents an orbital containing 6 electrons? I'm betting that's C, as we've labeled up above.